Well, welcome for this afternoon session. And Steffi, thank you very much for inviting me here. It's a great pleasure. First time DLL or DLD. And you should see the next two talks in connection, because I will emphasize differences between real brains and artificial brains, and Demis will demonstrate the marvels that can now be achieved with artificial brains. Actually, the order would have been better if it had been reversed, but Demis had constraints with the planes. So, relations matter, both in artificial and natural intelligence, because relations determine the essence of objects, of composite structures. Therefore, all cognitive systems, artificial or natural, they need very efficient strategies to encode, store, and classify relations between parts. And the common strategy is, of course, convergence. To have, if one has two parts, information about the two parts convert on a third party. And this is done very perfectly in simple nervous systems, like in insects or in invertebrates. And it's also a common strategy in AI systems, as you will see after Demis' talk, especially in the deep learning network systems. So a typical feed-forward network consists of an input layer, A and B, where the objects are encoded, or the components of objects. And then information is distributed on a layer of neurons or switching elements that can integrate information. And from there, it is then fed into a classifier level where activity is measured and the weights of the connections are adjusted such that a particular relation between A and B leads to a particular output signal at the classifier level, which is depicted in red here. So relations are encoded and also detected by convergent connections that are permutated in order to take care of many different possible relations in a complex system. This is very much the same architecture as it is realized in these deep learning architectures. One has a feed-forward network from an input layer at the left. Signals are distributed through diverging and converging pathways on subsequent layers until at the end there is a classifier layer. And what happens during learning is that the gain, the efficiency of these feed-forward connections that are recombined is adjusted so that a particular input pattern gives rise to a desired output pattern. Now, to some extent, the nervous system is built in the same way. We have always been intuitively thinking that it was a hierarchical system, and on the top there be the seat of the self that decides, perceives, etc. So there are certain similarities between these artificial systems and the way we thought the brain would work. So the question was, have we now understood the brain because we have understood these technical systems and they are extremely performing? And the answer is no, we have not, because the brain has invented, or evolution has invented, different additional strategies that make this little organ so extremely energy efficient. Consider this only consumes the energy of a light bulb, 30, 40 watts. And it's extremely fast, despite the fact that the neurons are extremely slow. So there must be some other principles of organization realized, and evolution has detected them. And we found out over the last decades that our concepts on how we think the brain works differ radically from how it is actually organized by nature. We found, first of all, an unexpectedly high density of interconnections. 70% of all the nodes in the nervous system, i.e. neurons, are connected with each other. This is surprising. Then we see a prevalence of reciprocal connections. Mind you, in these systems that I just described, you have feed-forward connections, serial processing. In the brain, you have more feedback connections than feed-forward connections. And you have, at every level, you have massive recurrent connections between neurons. So A feeds to B, B feeds back to A, and so on. We'll give you an example. And then there's much less hierarchy as we had thought. It's a highly distributed system. And because of this connectivity, the brain develops an exceedingly complex nonlinear dynamics that is unimaginably complex and high-dimensional. We have no intuition for this, and I will come back to that. This is how it looks from outside. If one looks on the cerebral cortex, one sees in human subjects something like 120 different areas. Each of these areas is has very much the same intrinsic organization, so it performs the same computations over and over again, but it is fed with different information. So some of the areas deal with vision, others with sound, yet others with touch, yet others with planning for the future and so forth. Now, what is interesting is to analyze the way in which these areas are interconnected. And this shows a mind-boggling complexity. The red dots that you see in these graphs, I hope you can see them. Oh, yeah. They now stand for one of these cerebral cortex areas. And the white fibers, the white lines, they stand for massive projections made out of neuronal processes. These are the wires, the telephone wires that interconnect those neurons in these areas. And what you see is a huge amount of reciprocity. There is distribution of signals from the input stage onto, in the visual system. There's only the visual system of the brain here with a few executive structures, so it's only a small part of a monkey brain. Information is distributed onto a first level of layers, of areas, but from then on, the principle of reciprocity and feedback prevails all the way up. And there's a very soft hierarchy, and one can see this by the fact that one can get from any particular neuron to any other neuron in this system with only one switching station if one knows one's way. And this principle is certainly true also in the human brain. One can now non-invasively trace the connections in the human brain, and one gets these wonderful pictures that attract the attention of artists, of course. Now, there are limitations to these feed-forward networks that I have delineated in the very beginning. They are not able to superimpose subsequent states because they have very limited memory function. They therefore have difficulties to handle sequences. It's difficult for them to handle a sequence like a speech sequence. And they lack the ability, and this is probably the most important feature, of self-organization. They are not generative. And therefore they lack all the advantages of self-organizing systems, and I will come back to that as well. Here is what evolution invented when the cerebral cortex came into the play, which was at the level of lower vertebrates. We now have neurons spread out in a layer that are all reciprocally connected in a very sophisticated way through pathways that all have adaptive synapses. They can learn. Neurons start to couple more if they are very often active in correlation, and they decouple if they are active in decorrelation. So signals are fed into these recurrently coupled networks. They develop an exceedingly complex dynamics. Computations are performed in this high-dimensional space, and then classification of these activity patterns is performed again in a fairly simple linear way. So it's this transformation from low dimensions into high dimensions and back transformation into low dimensions that makes the charm of the system. And if one looks at the connectivity of the cerebral cortex, you see these green pyramids. These are cells, and their connections impinge on their neighbors and vice versa. All these connections are reciprocal. And these reciprocal connections make up for the vast amount of connections that you find in the cerebral cortex. This is the meshwork that you can reconstruct from electron microscopic pictures. Mind you that in 1 cubic millimeter of cerebral cortex you have 6 kilometers of cable. And most of these are these reciprocal connections that link neurons among each other. So the hypothesis that we are currently putting forward is that with the evolution of neocortex, a novel computational strategy has been realized that capitalizes on the unique dynamics of recurrent networks. In some parts, branches of artificial intelligence, recurrent networks are now starting to be explored, and they already now show their capabilities. And we believe that because of this trick that evolution found fairly early on, that this is the success story for cortical structures. The price you pay is epilepsy, because these systems have the risk of runaway, but apparently the advantages outperform by far this risk. And nature has found ways to control this runaway dynamics. And you see the success story when the cerebral cortex is discovered for the first time at the level of lower vertebrates. Here, opossum, I think, is depicted. The only thing that has changed during the evolution of brains is the volume of this structure, together with the cerebellum and a few service structures that the cortex needs in order to be happy. But everything that distinguishes us from the non-culture building next neighbors, the apes and the monkeys, is just more of the same. This is a remarkable fact, not always easy to digest. Now, what makes recurrent networks so special? It's their ability to engage in very complex, high-dimensional nonlinear dynamics. You can imagine this. If all the elements talk to each other all the time, whatever happens somewhere will influence what happens elsewhere, and vice versa. And then they can self-organize. And self-organization is one important attribute of resilience, of robustness, or of the ability to self-repair. And these self-organizing systems can do this. The dynamics of recurrent networks, as I already said, they provide extremely high-dimensional state space in which one can store a lot of memories. They have fading memory. They remember what has happened because the activity circulates in the circuits for a while. And this permits to superimpose a lot of information and memories in the same network and have them simultaneously available for readout, which allows for parallel search and extremely fast readout. You can remember or you can find a content on the fly within a few hundred milliseconds, irrespective of whether it has been stored early in development or yesterday night. Then it allows for ultra-fast matching of input signals with memories. And this is what we have to do all the time when we perceive, because we take the sensory signals, compare them with what we know about the world, and this is done within a few hundred milliseconds in order to interpret complex scenes as this one. I use my a priori knowledge, which is stored in these networks, match it with the incoming signals in this high-dimensional space, and then I have the result. This is my perception. It allows for the encoding of sequences because it allows for the superposition of states to remember. Because it has this very high-dimensional space, one can put a lot of different patterns there and distinguish them because they won't overlap in high-dimensional space, even though they would overlap in low-dimensional space. So they are spread apart in this big space. And then, as already said several times, the ability to self-organize, which is so important because these systems show graceful degradation. If one takes out a few neurons or cuts a few connections, they will just continue to work or compensate for it. Now, the challenge that we have, if we want to use this principle in future computer generations, which I think will be a sine qua non after a while, one can still simulate these recurrent networks in conventional von Neumann computers. It's very cumbersome, very energy inefficient. What would be more advantageous, but this is a technical challenge, is to develop hardware components that have the functions of neuronal connections, of synapses, and the integrative abilities of neurons. And when I say synapses, I mean adaptive synapses, synapses that can change their gain as a function of history. And if we implement at some stage those hardware components into artificial systems, we will get at the energy efficiency that we would like to have. We would be even faster because then we would have fast switching elements. Electronics is much faster, or light computing is also faster. And they would be able to do unsupervised learning, which is something that nature capitalizes on a lot. Now, this principle that I just presented to you is ubiquitous in living systems because definition of relations matters at all levels, between the genes, between the proteins, between the organs. What makes you unique is the relations of the components, not the components. And because of the ability to self-repair, which for organisms is extremely important if they want to survive. So here you see a network that very much looks like a network of cortical neurons, but now it's genes. Genes interact with each other in a very, very sophisticated way. And even though we now have all the genes that code for proteins, we have understood nothing about the about the way in which the genes are orchestrated in order to generate a fruit fly on one side and a human being on the other. And this orchestration is a matter of defining relations between the genes, when they are expressed and how they interact. And these are the networks that control this. Poorly understood. Similar networks for the protein interactions in living cells. Again, the same motif of architecture. Call them small world networks or rich club networks or what have you. Reciprocity is what matters. Now, there is a drama, and let me finish on that. Because of evolutionary constraints, we have absolutely no intuition for these nonlinear, high-dimensional dynamics of complex systems, because we did not have to know about them in order to get along in daily life in this low-dimensional, macroscopic world. Therefore, we have wrong assumptions on how the world works. We assume linearity, because this allows you to make predictions. We think that the systems that we are dwelling in are predictable in the future and that they are controllable. And all these are illusions. And we also believe in the robustness of hierarchical structures, because we are monkeys. All these assumptions are no longer valid in the complex world that we have built by now. And here's just an example of a network of interacting companies, and you see again the same motif. These interactions develop a very high-dimensional nonlinear dynamics. And we still believe that we can control this, and we know that this is not possible. So my question to you is, are the problems with the management of complex systems that we have actually everywhere in the moment caused by these false intuitions? And these are too much confidence in top-down control and dirigistic interventions, because that doesn't work with self-organizing systems. They will do something, but not exactly what you want. And it may be also the uneasiness that we feel come from the lack of confidence in the efficiency and resilience of self-organizing systems, because we are part of self-organizing systems. We are only here because they are so resilient. So if we have more confidence in them and less confidence in the dirigistic intelligence or meta-intelligence of CEOs and politicians, etc., we might get away more peacefully. Thank you.